Let's look at an example of an oxidase. In this example, we're going to look at D-amino acid oxidase, DAAO. This is a hydride mechanism. It was originally believed to be a carbanion mechanism, but recent evidence and based on X-ray crystal structure has indicated it's likely a hydride mechanism. D-amino acid oxidase, or DAAO, is it's important in microbial metabolism. Okay, recall that mammals typically utilize L-amino acids. We don't typically utilize D-amino acids. Now, some bacteria and other microorganisms use the D-amino acids, so they're obviously important in metabolism for those species. It's also important in the regulation of the nervous system, and it's also believed to be important in aging in mammals. Okay. So let's take a look at the mechanism. So this is the structure of FAD. It's FAD right there. Okay. And I also drew in here an amino acid. I don't know if this is D or L. I didn't worry about it. I just drew an amino acid in. And then there's a serine residue that's in the active site. And there's also a water molecule that's trapped in this active site. This water molecule is believed to not diffuse in and out. It's kind of trapped there for the period of the reaction, typically. So in the first step, what's believed to happen is that water molecule deprotonates a serine, and then that serine deprotonates the zwitterionic amino acid. Those electrons off the proton on the amino group fall in and transfer this hydride to the nitrogen of FAD, pushing these electrons up into the nitrogen there like that. As a result of this first step, the oxidized amino acid is formed. So this is the oxidized substrate, the D-amino acid that's been oxidized. We'll talk about the fate of that in a little bit. So now all that needs to be accomplished is to reoxidize the FAD, or the reduced FAD, back to its oxidized form. Okay. And so, like I said earlier, typically oxidases use oxygen, molecular oxygen, as the acceptor. Now I have molecular oxygen drawn here in its triplet state. You can see the two unpaired electrons here and here. Okay. What's believed to happen now is these electrons here on the FAD fall back down in, and one of these electrons goes onto this carbon here, and the other electron is transferred to the molecular oxygen. What that does is that generates a radical intermediate, okay, and also what's called superoxide. Now, superoxide is typically not basic enough to be protonated by water, but it is a good nucleophile. And what ends up happening is it ends up reacting with this electron here to form this oxygen. This single radical electron here reacts with this single electron to form a bond between this carbon and this oxygen. And then the anionic character transfers to this oxygen and gets protonated by one of the the proton on the water that originally deprotonated the serine. Okay. That makes a hydroperoxide flavin intermediate. Now, this hydroperoxide flavin intermediate, it undergoes an elimination reaction, and the mechanism occurs as follows. Okay, so it's essentially an intramolecular elimination reaction. What happens is these electrons fall into here, and as this oxygen deprotonates here, that regenerates our FAD, generates peroxide, the reduced form of molecular oxygen, and again we still have our oxidized D-amino acid, which has become an iminium ion. This is an iminium ion, as we said earlier. Now, iminium ions are like imines. They hydrolyze under aqueous conditions. And this reaction, this hydrolysis, is not believed to occur in the enzyme. The iminium ion gets ejected from the active site, and then when it's in an aqueous environment, it hydrolyzes. You'll recall that imines hydrolyze to a ketone or aldehyde from which they came from, and the amine, in this case ammonia. So that's basically the mechanism of how DAAO operates.